Yeah.
Great. You can just share your slide. Okay. So before going into the talk, very interesting talk. So first of that, I want to introduce brief introductions about the Prof. Hom. His title of keynote 2 presentation is Morphological Characterizations and Properties of Leaf Sheath, Dead Palm Fiber, Biomass-Based Reinforced Biocomposite Potential for Lightweight Structural Application. Prof. Hom Dhakal is a professor of mechanical engineering at the School of Mechanical and Design Engineering, University of Portsmouth, UK. In addition, he is also a docent, visiting professor of biobased material at Faculty of Textile Engineering and Business, University of Borås, Sweden. He leads the Advanced Polymer and Composite Research Group within the School of Mechanical and Design Engineering. His principal research interest lies in the design, development, testing, and characterization of suitable lightweight composites, nanocomposite, natural fiber composites, and biocomposite, including their mechanical, thermal, and environmental property. He is also fellow of Higher Education Academy, chartered engineer, and a fellow of Institutions of Engineering and Technology, fellow of the Institute of Material, Minerals, and Mining, and a member of American Society for Composites. Professor Dhakal is the co-author of over 150 publications in the areas of lightweight sustainable composites and biomass that attracted well over more than 3,900 citations with H index of 31 and I-10 index of 62. Welcome, Dr. Hom.
And Dr. Javed, thank you so much for your kind introduction. I feel greatly honored to be here, and thank you so much for the organizing committee for giving me this opportunity. And it's so great to be in this amazing conference, and the work that you have put in background is just much appreciated.
Thank you.
But I hope you can all see my screen.
Yes, your screen is
okay.
Yes.
Right.
As the title says, just make the what called the full screen. If not full, that.
Okay, it's not full. Okay, let me just.
I don't know, Miss Troy. You just check. I think already full that time. Sorry, that it's already full that time.
Is it full now?
Yeah, it's visible, but I think the earlier version is better. That you go back to that. Because that is bigger if you
okay, right. So is it okay now?
No, Dr. Hom, you can make the full screen because it's showing the second slide also in that. So you just show the.
Okay, let me just go back and let me see if I can do something. I did something and then
otherwise
okay.
You can go there. It's no problem.
All right. Whether this gives. Does this give full?
Yeah, this is full, but it's showing the next animation also in that case.
Okay.
Close that next animation and show the full first screen.
Okay, let me just see if next I can close the next animation.
Yeah, close that one. Yeah, right.
All right. Let me just see. I have no idea what has gone.
It's
okay, right.
It's okay.
Yeah,
no
again,
let's go.
Thank you so much. Yeah, thank you so much for this wonderful opportunity. As Dr. Javed mentioned, the title, Morphological Characterization and Properties of Leaf, Sheath, Dead Palm Fiber, Biomass, Waste Reinforced Composite. So today I'll be sharing mainly a little bit of context and linking to sustainable materials, and then obviously value creation through sustainable materials. Then I'll be talking a little bit about natural fiber composites, how that can help us to move sustainability. Then also the key topic is morphological characterization of dead palm fibers. Then obviously some of the key properties of dead palm fibers and composites and some discussion. Then I'll be also looking some potential application of dead palm fibers and some new advances, how we can make dead palm fiber more compatible to the industrial need, how we can improve the performance, and then conclusion. So I'm just putting the context. The threat of climate change due to human activities, the agenda for sustainable development is set to become a global top agenda. If we look this slide, the plastic uses, for example, or plastic production has gone 20-fold over the last 50 years, from 15 million tons to 311 million tons in 2014 to 1964. And if we look at plastic packaging alone here, most of the materials are linear cycle. They don't go to circular cycle. So most of them are either thrown to the landfill or gone to the marine environment. Very small amount is recycled, such as 8% is recycled, 4% process losses there, 2% closed loop recycling. So the overall picture is that we are creating huge amount of plastics, but we are not recycling them enough. So just looking the scenario of plastic packaging, you can see here 46% of materials are used in packaging materials, and the use of plastic generated by industrial sector in 2018. So you can see a textile, and then obviously there are other areas, transportation or building and construction. The packaging is the big area that consumes plastics. So going back to that diagram.
Dr. Hom,
from this huge amount of utilization.
Dr. Hom, just a minute. I think the
can you click on the presentation? Can you click on the presentation? Right click on the presentation and then select the hide presenter view.
Yeah, hide presentation view.
Is it okay now?
Yes, very nice, very nice.
Thank you, Dr. Midani. Thank you so much.
Thank you so much.
Okay, wonderful. Right. So, all right. So let me move this a little bit in the corner. If I can take this a little bit in the corner. No, I cannot. Okay, let me just go back here. Sorry. All right. Let me go back here again. Yeah, this was the slide I was in. Thank you so much, Dr. Midani, for your help. Okay, I hope you can still hear me and you can still see the screen.
Yes. It's clear. Okay. Everything clear now.
So the new plastic economy from Ellen MacArthur Foundation, they are just next to our Portsmouth. They are based in the Isle of Wight. They have done amazing work in plastic recycling and so on. So one of our courses and some of our initiatives are recognized by Ellen MacArthur Foundation. So that is always very great and really appreciative. So what we are trying to do is less to the landfill, less to the marine environment, recycle them, bring them in a circular economy rather than linear circle. So that is what is expected here. So if we talk about sustainability and sustainable development, I'm trying to link our material research into sustainability. So that is my point here. So development that meets the needs of the present generation without compromising the ability of future generations to meet their needs. That is the definition, very key definition of sustainable development. So sustainability means we need to have resources that are sustainable. We need to use them in a way that they are left for our future generation. So there are different sustainable development goals. Whenever I do research, whenever I select materials, try to talk to my colleagues that, okay, which sustainable development goals that our research contributes? Is it the global warming, or is it the environmental aspect, or is it the energy aspect? So it is always good to think about sustainability and sustainable development when you are doing material research. This is just a very quick overview again. The way we are consuming materials is just unsustainable. The today's rate, you can see here, is just not sustainable. If we consumption with increased efficiency, we can bring this down, but a required consumption rate is this, and this is the sustainable rate. So how do we do that? That's the challenge. And if we look the climate, recent climate change, we have been, bushfire, flooding in Europe and flooding in the USA, and so many things happening. The climate, the temperature rise, and so on, has caused a massive kind of awareness that our current research, our current has to be directed towards sustainability. So that's what I would like to just share from this particular slide. So social aspect, environmental aspect, and economic aspects are very important when we are obviously looking sustainable materials. I still have some problem looking on my right-hand side of the slide, but it's okay. Right. So here again, the Alan MacArthur Foundation slide. I like this very much. How we can.
I think you can. I mean, you can minimize your screen and the other presenter screen, or you can click on top view. You can make a side-by-side view.
Yeah, if I can hide the some. Okay, if I okay.
You can hide.
Yes. Now it works. Perfect. Okay, wonderful. Thank you. So again, here, how we can, finite materials, how can we use again and again and again? That is the circular economy approach. And then how we can extract material in a sustainable way. Then we can cascade them in a consumer. So this is another example of spider diagram. They call it sustainable development and circular economy approach. And then if we look on the solid waste management hierarchy, obviously we want to reduce the source material, try to reuse it and recycle it, and the resource recovery through incineration perhaps, and then very little amount of material should go to landfilling. So most preferred option is resource reduction, reuse, and least preferred option is incineration or landfilling. So sustainable materials and value creation. Well, composite materials are a combination of at least 2 or more materials. I think we are working in the composite materials. I don't think I need to go more on that. Obviously, composites are lightweight, high strength to weight ratio. That is specific properties. That is what attracts us working on composite materials. Then obviously there are corrosion resistance material, and their design flexibility and excellent fatigue endurance attracts designers and engineers to use composite materials. So here I have just put some application of natural fiber reinforced composites, which jet palm fiber also comes within that. So there are many advantages. So again, I don't need to go too much on detail on that. Obviously, biodegradable is a big attractive attribute. Sometimes we also look biodegradability to long-term durability. If material is very biodegradable, when you talk about automotive industries, they say, when you say biodegradable, they say, oh, is it strong enough? Is it durable enough? Can it withstand long-term durability? That's how they ask. But obviously, biodegradability means materials biodegradable in certain conditions. Using less energy, renewable sources, obviously low density and high specific properties, cost effectiveness, low risk to human health. If you work glass fiber composite and flax fiber composite, for example, glass fiber composite will create a lot of skin irritation and you need to pay a lot of attention on health and safety. Whereas if you work with flax fiber composite, there is no risk of such skin irritation and so on. There are so many applications we can think of natural fiber composite, but so far there are they are used in low load bearing applications, in automotive industries, in many other applications. So advantages and drawbacks, I think we can quickly look on that. Advantage: specific strength and stiffness, low hazardous manufacturing, low processing energy, low cost of manufacturing, low toxic materials, non-abrasive, low risk to human. Obviously, drawbacks is the moisture absorption is a big drawback of natural fiber composites, and lower durability, and then obviously their inferior long-term durability compared to conventional composite, and their performance sometimes is not obviously as strong as conventional material. And then obviously there are less standard available, low thermal stability, and obviously lower flame retardancy behavior. And then obviously overall the variability of properties are challenging. So if I move to the next slide, obviously I'm not staying long here, but nonetheless here the positive contribution towards environment is the key attributes of natural fiber reinforced composites. So materials, they are sustainable, they are multifunctional. Sometimes we can get multifunctionality from natural fiber composite. Lightweight, obviously, as I mentioned, low hazardous material. The interesting thing is in the table here: flax, hemp, jute, jet palm fiber, and e-glass. If we compare these different materials, commonly used natural fibers, flax, hemp, jute, kenaf, and other materials are there, obviously. And if we look jet palm fiber and e-glass, so density, we can see 1.14 to 1.5 for flax, whereas e-glass 2.54. If we look density of dead palm fiber 0.92, less than 1, which is very attractive attributes. And then if you go to strength, obviously not so strong dead palm fiber compared to flax and hemp. And then, but if you look the specific strength divided by density, so dead palm fiber has 242, which is not too bad, and then modulus is 9.23. Obviously, it's a lot lower than flax and hemp, but nonetheless, it's quite interesting feature here. So we'll keep that in mind when we talk about dead palm fiber. Looking on nasal fibers again, we have okay. Let me just try to move this one somewhere if I can. Okay, I can. Bear with me. I'm just trying to make my screen as clear as possible. No, I might have lost my previous slide. Okay. No, I cannot. Okay, right. So we have price and energy. Looking on flax fiber, looking on glass fiber, and looking on carbon fiber. Flax fiber has got competitive price and low energy consumption compared to glass fiber and carbon fiber. That is the summary of this table. Okay, so application-wise, obviously there are different applications we can. These materials have been utilized. Aerospace, obviously, demand for lower emissions. I'm talking about composite materials. Marine glass fiber and polyester resin for boat hulls, decks, and superstructures. Function, quality, and cost is very important for marine sector. Wind turbine, as renewable energy sector, they use. They are using flax fiber. They are trying to replace glass fiber turbine blades with flax fiber turbine blade. So automotive industry, obviously, low carbon economy, lower fuel emission, and lower running cost is driving them to use lightweight composite materials. And then obviously construction sector are also looking lightweight composite materials. So when you say lightweight composite materials, obviously glass fiber, carbon fiber, and then natural fibers are there. So what are the drivers or motivation for the lightweighting? Obviously, the transportation sector shares about 25% of global energy related to greenhouse gas emission. So greenhouse gases obviously coming from transport are these very dangerous, hazardous greenhouse gases. So OEMs, original equipment manufacturers, are moving towards lightweight vehicles, weight reduction, less fuel consumption, and then that leads to less CO2 emission. Obviously, the composite materials are 35% lighter than aluminum and 60% lighter than steel. And the use of composite in automotive, for example, can lead an overall vehicle weight reduction up to by 10%. So these are the drivers for using lightweighting or lightweight materials. So this slide will just give us some kind of perspective in terms of looking lightweighting materials as well as their environmental credibility. So let me check my time. Okay, I have not much time left, so I need to move faster. So obviously LCA, if we look at biocomposite and composite, biocomposite has better environmental credibility than compared to glass fiber in terms of materials, transport, manufacturing, use, and end of life. So these are the 5 different categories we use in life cycle analysis, comparing these 2 materials. So lightweighting involves design of composite fiber geometry, end of life, materials, multifunctionality, cycle time reduction, and so on. Obviously, when we look characterization here, obviously structure, processing, properties, performance are linked. If we use hand lab method, we have got high variability, high void content, maybe less mechanical property. If we use compressor molding, it will be better mechanical performance and then less void content. If you go to RTM, it will be even given better mechanical performance. So different structures. So processing properties, performance, and structure are linked together, and then characterization is important. Here, just an example. We can see a stress and Young's modulus of a natural fiber. When diameter is increased, the strength and modulus is decreased. We talk about aspect ratio, length and the diameter coming into play. So in Portsmouth, in our research group, we were looking some dead palm fibers. So we have just given some name SD1, SD2, SD3, 4, and 5. So we're just looking at dead palm fibers coming from leaf, coming from steam, and coming from different parts will give you different diameter. and that different diameter gives you different properties. So if we look up a jute fiber and then raw jet palm fiber, you can see diameter variation is significantly high compared to other commonly used natural fiber composites. So again, morphological characterization, understanding what is going on the property is very important. So you can see a lot of porous structure for jet palm fiber. On the left-hand side, this was done in our research group. We looked at the SEM of the fiber and the surface morphology, and this was from this particular source I obtained. So as there are different methods available for surface modification of natural fibers, so obviously using sodium hydroxide is very commonly used technique. Different percentages are used. Sometimes maybe 5% is the best, sometimes 3% is the best. So again, we can improve the properties by using surface treatment. So this will give us moisture absorption. Here we have two curves on the right hand side. One is PCL and hemp fiber. On the left hand side, we have got jet palm fiber with high density polyethylene and PVC. So you can see here, jet palm fiber has one attractive attribute, that is less moisture absorption compared to other natural fibers such as hemp and flax. So thermal stability, obviously this curves, okay. So we are looking at thermal stability of jet palm fiber. One of the attractive attributes of the jet palm fiber, it has got high thermal stability compared to other flax, hemp, and other natural fibers, which is attractive attributes. I don't have time to go detail on this one. So mechanical performance wise, not great. Tensile strength about 25, close to 25, and modulus close to 4. Impact strength quite good. So our challenge is this: when you are trying to use jet palm fiber for different applications, the challenge is the strength and modulus. If we are trying to use for semi-structural application or non-structural application. So I'm not going to go too much on this one. So I want to move. How can we reduce the mass? So that is, so using lightweighting approach can help to reduce maximum big amount of CO2 in automotive sector. Right. So I want to just quickly go what we are doing in our research group in terms of working on jet palm fiber. So obviously we work with flax fiber, we work with some conventional composites such as glass fiber, carbon fiber to be used in aerospace application. In this particular case, we have got in autoclave and out of autoclave technique used for manufacturing of carbon fiber composite to be used in fuselage in aircraft. And then here we have got flax fiber, we have got some 3D printed parts, and we look on modeling and damage characterization. So here I want to present one particular work that we did in jet palm fiber, composite we made. We looked, obviously we have the fiber, we chopped them in a small size, and then we characterized their properties, and then we looked their mechanical strength, tensile strength, and modulus. Then we looked impact toughness behavior, which is really good. The jet palm fiber PCL gave quite good impact toughness compared to hemp fiber. You can see the right-hand side hemp fiber, left-hand side jet palm fiber PCL. We use two different types of energy, incident energy, 50 joules and 25 joules. And this gives quite good impact of its behavior because jet palm fiber has got elongation, higher elongation compared to other material, other commonly used natural fibers. So as we saw the fiber matrix interface, obviously interface was not amazingly great. Maybe that was why we obtained high toughness behavior. If you are trying to get a higher mechanical strength and stiffness, obviously your interface has to be good. So you can use some other treatment available for us to increase that. So processing parameters and the fiber geometry and diameter influences overall mechanical properties of jet palm fiber composite or any other natural fiber reinforced composite. So here is a challenge for us that I want to put forward to you. We are working on flax fiber PLA, flax fiber PHA, and flax PP and flax PBS. So for flax PLA, getting 100 megapascal of strength was massive achievement. That was obtained by optimized fiber geometry, optimized manufacturing process, and optimized fiber matrix addition. So if we can get that flax PLA 100 megapascal, this is really a good sign. For jet palm fiber, and biodegradable polymers. We are far away from that, but provided if we use different available technique, we might be able to increase that properties. Here, Professor Zaida and team has done very good job. The dead palm fiber and dead palm fiber bamboo hybrid composite, and trying to enhance the mechanical properties. So using hybrid technique can be very good approach to enhance the mechanical properties of dead palm fiber reinforced composite. Here we have used flax fiber, and we have used stitch and non-stitch, and we have used basal fiber to hybridize and trying to understand mode 1 fracture toughness behavior flax fiber, which has helped to enhance the fracture toughness behavior mode 1 and mode 2. So there is another approach. Obviously, we can use fiber metal laminates, but maybe this is a bit far away for dead palm fiber. Some flax fiber has been used in this approach. So moving forward, I'm closing very soon. Dead palm fiber, flax, hemp, bamboo, silk, we compare. The thermal stability of dead palm fiber is very encouraging. As you can see, DTC curve about 450 is a very, very big attraction for us to be used in a processing window using thermoplastic materials. So we can use enhanced manufacturing technique to enhance mechanical performance. That is what we have been doing for other commonly used natural fibers.
Dr. Hom, sorry to disturb you. Try to be. We are getting late, so try to be.
I finished that.
Sorry.
And then we have got characterization technique.
Okay. Thank
Understanding the mechanical behavior, what happens, failure behavior using X-ray microscopy, and the conclusion. Obviously, we need sustainable materials. Bio-based composite is a solution. Dead palm fiber can be a very good material, but the mechanical performance is still a long way to go. But we can use certain approach to enhance this behavior. Obviously, challenges, obviously, the designing, manufacturing, and other aspects coming with that. Thank you so much for your attention. I'm so sorry taking a bit longer time, Professor Zavid.
No problem. Very, very interesting talk on the biocomposite sides. You know, there are a lot of people from the biocomposite. Now we open the floor. If any 1 or 2 questions, we can share, ask with him. Otherwise, later on you can contact with him and further communications.